Hi everyone, it's me, Carolyn, and we are continuing our look at looking between two different populations. In this video, we will be looking at two completely different populations. The last video I did was matched pairs. This one, they will not be connected in any way. So let's go to our guided notes here. All right. And this is 11.3 of our textbook. And we are going to be looking about the inferences of two means, independent samples, which means we need to have the following situations. First of all, as always, the samples have to be obtained using simple random sampling. We want to make sure that these samples were done in a best practices kind of situation. We want to make sure that the samples are independent, which meaning those in the first sample do not affect or have no bearing on who is in the second sample. We want to make sure that both populations are relatively normal with no outliers, or that the samples are large enough. So we need to have both samples being large enough. Now, there are multiple different ways of looking at two different samples, and our textbook does go through a bunch of different ways about how we can pool the variances together. We can assume that they're different. We can assume that they're the same. So there's a lot of different tests that are out there. Like we've been just touching on a little bit of everything. So you can kind of just realize that, hey, there are different tests out there. This is the one that we're going to be using in here. Now, if you were to go into this field in the real world, you would do a lot more delicate procedures to make sure that you're doing the right stuff. And also you'd be learning all the differences between them. Here, we're just giving you a little bit of a taste of everything. All right, so here's our formulas that we have. So first of all, if you wanted that confidence interval, that 99% confidence interval, so alpha being 0.01, this is our formula that we have. So we have the mean of the first set, subtracting off the mean of the second. So we're kind of trying to find about how different they are. Again, we add and subtract t alpha over 2. And we've talked about a t before. It can come from our table. In this video, I will be going directly to StatCrunch to get most of our information. Just variance, notice it is squared, so it is the variance and not the standard deviation over n1 plus the variance of the second sample over n2. Those are both divided first, then added, then square root. So make sure if you're doing this by hand, you do follow the correct order of operations. Now, also we need to remember that our samples might not be the same sizes. So our degrees of freedom is going to be the smaller of n1 minus 1 or n2 minus 1. This is to make sure we err on being overcautious. Okay. Our steps for hypothesis testing are very similar to those that we've seen before. We will write the hypothesis mu1 is equal to mu2, or you could move that one over and set it equal to 0. Our alternative will be either the less than symbol, the greater than symbol, or the equal symbol, not equal symbol, depending on what we're testing. Are we thinking, is it bigger, is it smaller, are they different kind of things? We will be looking for our alpha level. Again, in our course, that's going to be stated in our problems. In the real world, the statisticians and everyone else decides what that level will be. Our test statistic is very similar to what we have in that confidence interval. You'll see this mu1 or x bar 1 minus x bar 2 minus this mu1 minus mu2. That for our hypotheses is 0. So we actually do have a 0 in here. Again, the variance of the first sample divided by the sample size, the variance of the second sample divided by the sample size, that all should be underneath that square root symbol. So that's our step 3. Step 4, as we've seen in the past, we find the critical values which are associated with the alpha. We usually got those off a table. We will be using StatCrunch, or we get the p-value that kind of goes along with this. Okay, and once we have those, we can describe, decide to reject or not reject, and then write our conclusion. So depending on, did our test statistics fall, where did it fall within our critical values? Was it in that critical region or that rejection region that I like to call it? Or we compare our p-value to our alpha value and we write our conclusion. I do have one example for us. And I did use data this time, so you just can kind of see the difference. We've used summaries in the past, but we have that a student wanted to determine if the wait time at the drive-in or the drive-through at McDonald's was faster than the drive-through at Wendy's. So what they did is they gathered two simple random samples of 30 wait times at McDonald's, 27 wait times at Wendy's. And here are their results. So we have a lot of times. Notice the times are in seconds. Otherwise, we'd be waiting a really, really long time for our food if those were in minutes. All right. So first of all, we're going to do a couple of different things. We're going to kind of go through this. The sample size of Wendy's, notice it is less than 30. But we are going to notice also that there really isn't any data that's completely out of the norm. This 471 is a little large, but it is not so large compared to all of the data that we don't really have any outliers. So we're going to just assume that it's okay, and we're just going to go with it. Is the sampling method dependent or independent? Provided they did a good job of choosing these samples, they weren't like actual same people going from one to the other, we should be fine. They did say it was a simple random samples, so these guys are going to be independent from each other because the people that attended here did not attend here or vice versa. And also we don't have the same sample size, so we know that that is not the case. Our variable of interest, well, that is the wait time. How long did they wait? Is it qualitative or quantitative? Kind of some review here. Qualitative is a non-numerical method. Quantitative is numerical and measurable. This is quantitative because it is measurable. Okay, we're going to do a couple of things here, and I will do both of these as we're kind of in StatCrunch. Is the wait time at McDonald's faster? I should be less than, because faster would be less than that of Wendy's, and we're supposed to use alpha 0.05. And then we also want to find a confidence interval for that difference of times, just so that we can see the methods of doing so. All right, so we're going to first of all get ourselves set up for doing is the wait time less at McDonald's less than Wendy's. And that means we need to go through our 5 steps. So we have to write our hypothesis. Step number 1 is to write those hypotheses. And I'm going to say our mean of McDonald's starting is equal to the mean of Wendy's, or you could write it. And I did put M's and W's instead of 1s and 2s, just to help me know which way I'm subtracting. We want them to be faster, so that means our times will be less, smaller. Okay, or you would write this as less than 0, just so you kind of know. Our step 2 is at alpha level, and alpha was given to 0.05. Step 3 is our test statistic, which I from just make everything we need. Step 4 is those critical values. In this case, it will just be a critical value because we're looking one direction. We want this to be smaller, so we want this to be less than, so we'll be down here somewhere. Also want our p-value. And then we will do our decision and our conclusion. While I'm in StatCrunch, we also want that 90% confidence interval. I'll put 90% confidence interval right down here as well. So, okay, so I've got everything kind of ready, what I want. And I've also done some work ahead of time so that we don't have to watch me type all the data in. So I did go into StatCrunch earlier, And I typed in all of the McDonald's data and all of the Wendy's data in there. I also did relabel my columns. I just said McD and Wendy's so we knew which one was where. And now we're ready to get all of our information. And this is where StatCrunch and other technologies really can play a nice role in speeding up the calculations. Doing this all by hand is a lot of work. Just calculating the mean. If you did it by hand with just a calculator, adding all those values up and dividing by 30 or 27 would take some time. But we're going to go into our t-stats because it is a t-statistic. Okay, this is not a one sample because we do have two different samples. They are not paired because they're not a matched pair. This is just your simple two sample test. And we do have data. We don't have all the information, so we'll get this data. My sample one is in the column McD. Sample 2 is in the column Wendy's. Okay, we are doing our hypothesis test, mu1, and we want it to be less than 0. Hence the reason I wrote it in this format as well. Making sure the mu1 is McDonald's minus my Wendy's, and I want the less than 0. So sometimes starting off with them on either side and then shifting them to the one side is important to make sure you pick the right inequality here. Okay, so we also want to do our critical value. Maybe we'll do some summary statistics so we can kind of get some other information on here. So we'll get some more information. So, all right, and we are ready to calculate. So we'll slide this over. Sometimes it doesn't show all the details, like the samples. This is that extra piece in the middle. And I do that just so we can kind of see some of the standard deviations and things of that nature. Here is the differences, the information I need. Standard error, degrees of freedom is 32.88. They actually use a pooled type situation or a different type situation. If we were doing this one by hand completely, we would have used degrees of freedom being 26. The smaller of N1 and N2 minus 1. So 29 versus 26, we would have used 26. This program kind of does some computations between the two, but I'm going to pull our test statistic here. No matter what we did for the degrees of freedom and things like that, the test statistic would still be the same. So we get that negative 0.405. Our critical value is at negative 1.69. And then our p-value is 0.0001. Make sure I get enough zeros in there. All right, so I'm going to close this. Again, I went to all of the pieces. We're going to do it again because I need that confidence interval as well. All right, so I'm going into stats. T-stats, to sample with data. Sample 1 is McD. Sample 2 is Wendy's. We are not doing the hypothesis test this time. We are going to do a confidence interval, and I'm doing a 90% confidence interval just because that's a number I stuck. And I could show the statistics. It'll show the same ones as we did before. I'm just going to calculate this and get my lower bound and my upper bound. You'll notice not much changes. We still have all the same information here. We just are now given that lower bound and the upper bound, which I will write down here. Our lower bound of 121.21 and our upper bound of negative 49.8. And I'll just go 2 decimals, 88. Again, it really doesn't matter which one, how many decimals you use, just kind of follow the directions. It would matter if this was a life or death situation, but it is not. So I'm going to go back to my guided notes so that we can finish writing this up here, finish our hypotheses and everything there. There we go. I got to wait for it to readjust. There we are. All right, so here's our test statistic that I pulled off of StatCrunch. Here's my critical value, there's my p-value. So I'm ready to make my decision and write my conclusions. Again, if you remember to make our decisions, if we had found the critical value, we then kind of put this into our picture, and a -4 is going to be down here somewhere. So there's my -4.06, well beyond, well into that critical rejection region. So we will be rejecting. Here we would see also be comparing our p-value to alpha value and see if it's smaller than alpha, which it is. Excuse me. So we would again be rejecting, which means we are not liking that statement. We are kind of leaning towards this, saying that there is enough evidence to show that are shorter. At least. Which means if you want your food quickly, you're going to go to McDonald's versus Wendy's. But then again, if you really like that Frosty, you're still going to go to Wendy's. Anyway, enough about McDonald's and Wendy's. We also had our confidence interval, and this was not gotten to kind of reconfirm anything because we were doing only a one-tail test. If we were doing, are they different or not, we could have used this because we would have been looking for the 0. And you'll notice these are both negative. 0 is not in that interval, so we would reject anyway. You can kind of be a little bit careful. This was a alpha being 5%, so which is fine here. So if we had been doing a two-tail, putting 0.05 here, 90% would have been the one we should have been looking at, because that would have been 10% there. So 90% would have been the confidence interval we would have wanted to calculate if we had been doing a two-tail test, but we were not. So this kind of concludes all of our hypotheses testing for these types of situations. In our next videos that you're going to be seeing, we will be looking at a little bit different kind of information. We're going to be looking at things more in table format. So not so much numerical data. And again, we're just going to pick and choose a few topics to look at, but those will be in our other videos. So I will see you in the next video. Have a great day.